Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today we're on our enrichment lecture in Module 9 based on the calculator, which I call the calculator, the good, and the bad. And I was reading a magazine, in deference to our producer, I won't say which magazine it was, but there was a very lovely cartoon in there. And it showed hundreds of slaves rowing a Roman galley. And the slave master is standing over them with the whip. And he's saying to them, "Gentlemen, I have some good news for you and some bad news." He says, "The good news is the skipper has quadrupled your rum ration for today. And the bad news is that this afternoon he wants to go water skiing." Now, I think that's a very funny story in its own right, but it sort of typifies the story of the calculator. It's a good news, bad news story. It does some things for us in a very, very nice way. And on the other hand, there are certain things that if we don't know how to handle them, from what we've learned already in the course, the calculator will be of no help to us. And rather than just discuss this, I thought I'd go over to the board and just show you a few examples leading from the good into the bad. Okay? Let's start off again with a problem that hopefully is way beneath your dignity. At $2 each, how much will 4 pens cost? And you think nothing of this problem. You say, well, you're spending $2 4 times. The answer is $8. And if I say to you, you can't use your calculator, this certainly doesn't bother you. Now, compare that with the following problem. It says at $2.79 each, how much will 5,237 pens cost? Now, the thing that's interesting is that if you compare problems 1 and 2, you see the difference between difficult and tedious. 1 and 2 are exactly the same type. In both problems, you take the amount per pen and multiply by the number of pens. The difference is, in multiplying 2 by 4, it wasn't really a challenging problem at all. On the other hand, to multiply $2.79 by 5,237 can be a bit of a chore. See, it's not a hard problem. It's something we had done by the time we got to Chapter 3, Module 3 in our course. And even though we've passed the stage where I want to practice multiplication, I do want to try to give you the feeling over here for what kind of a problem you're letting yourself in for if you decide to have calculator anxiety. I've seen students tell me, I don't want to use the calculator, I feel better trusting pencil and paper, I don't trust the calculator. Fine, don't trust the calculator, just use it. The thing is, you can always check if you want to do things longhand, do them. If you do the thing on the calculator, you can always check them longhand. But the interesting thing is, if you have lots of things to do, the calculator will do for you in mathematics what the typewriter sort of does for handwriting. If you've got nothing worth saying, the typewriter won't make your statements any better. You see? And if you don't know what to do with the mathematics, the calculator won't help you. But if all it boils down to is the mechanics, see, the mechanics of writing, the mechanics of doing the arithmetic, the calculator can be a tremendous time-saving device. But at any rate, we could do the problem this way. And we find that the answer is $15,553.89. By the way, even when we do the problem the long way, there's no harm in estimating the answer. See, $2.97 is 3 cents less than $3. So feel free to use the distributive property. Multiply the 5,237 by 3, which is a relatively easy problem. That would tell you what the price would have been if they cost $3 each. Then multiply 5,237 by 3 cents. That's going to be the same 3 numbers, only with a different decimal point. Do this subtraction, and you get the same answer. And by the way, this is a good way to do the problem, even if you have a calculator. Because even with the calculator, you say, look, this is roughly 5,000 pens. This is roughly $3. So roughly the answer should be $15,000. And that's not a bad thing to know even when you're using the calculator, because it gives you an estimate of what kind of an answer you're looking for. It helps you guard against those mistakes that can be really tragic, so to speak. Now, I deliberately didn't bring a calculator with me today, other than for the fact that I couldn't afford one. But basically, the main reason I didn't bring the calculator is that calculators are quite different. Some calculators work one way, some calculators work another way. So basically, I will talk through with you the way my calculator works, which happens to be a TI-55 type of thing. It's fairly conventional. But basically, read the directions on your own calculator to make sure how these operations work. The heavy-duty part of using the calculator is in the supplement and the study guide. I just want to show you roughly what the calculator does for you. You see, in doing this problem on the calculator, all I would do, well, always make sure the calculator is on, of course. Enter the first number you want to multiply, the 5,237. Notice there's no dollar sign. You're going to have to keep track of the dimensions yourself. Then press the multiplication button, the one with the time sign. Then you enter 2.97. See, so far what you've done is the equivalent of 5,237 times 2.97. And by the way, that's how you enter the numbers in the calculator. Just like the cast in order of appearance. You press the 2, the decimal point, the 9, and the 7. You don't even have to keep track of decimals in this. Then you press the equal sign, and all of a sudden, this answer will light up. You see, as far as the calculator is concerned, it does not distinguish between this and the problem that says enter 4, press times, enter 2, press the equal sign. It would give you 8 for the answer. The difference is, as far as the calculator is concerned, it will do multi-digit problems just as easily as it will do single-digit problems. But if you were to do those two problems, one of them would be much more tedious than the other. And obviously, there are still some things you have to remember. On the calculator, all you'll see is 15,553.89. It has to be your decision to put the dollar sign in here. I have seen people put down pens rather than dollars. I've seen people use miles per hour because they were thinking of something else. The label usually is something you have to get for yourself on the calculator. As the number of digits increase, the value of the calculator becomes even more important. If I say, how much is 3.14167 times 5.09861? Notice that without the calculator, I have to multiply two 6-digit numbers. Again, it's not a bad idea to say that this number rounds off to 3 and that this number rounds off to 5 to the nearest whole number, so that I now know that I'm looking for an answer that's around 15. Now, what do? The same thing I did in problem number 2. I enter the first factor, that is, I press 3, decimal point, 14167. I then press the time sign. I then enter 5, decimal point, 09861. Press the equal sign, and the answer 16.018150008 lights up, at which point I can make the judgment as to where I will round this off. And by the way, how do I know that this answer here isn't exact already? It just occurred to me to mention that. You see, take a look. The leading digit here is a 7. The leading digit here is a 1. So when you multiply, the 1 is going to multiply the 7. 1 times 7 is 7. The fact that there's an 8 over here means that there was already an overload in the number of digits my calculator could give me, and it evidently has rounded off or truncated the answer. Another problem one has to deal with in dealing with a calculator. But basically, notice how this works. And that's nice. That really is the good news. It saves us a lot of problems. But the problems it saves us are only in the areas of mechanical computation. See, let me just show you an example that we've dealt with many, many times. All I'm going to do is rewrite problem number 3 slightly. What I'm going to do is to put the 5.09861 on the other side of an equal sign. And the problem is going to become, fill in the blank, 3.14167 times blank equals 5.09861. Now you see what makes this problem tough with the calculator is you can enter the 3.14167, you can enter the time sign, then you come running up to the instructor and say, hey, something's wrong with my calculator, there's no blank on it. In fact, you know, later in Module 12, when we talk about algebra, basically the difference between algebra and arithmetic is if you can do the problem directly as it's written on the calculator, we're going to call that an arithmetic problem. You see what I mean? In other words, in the previous problem, it was 3.14167 times 5.09861. I could have entered all of those into the calculator and get the answer. Notice in this problem, I have to recognize that what? that although this looks like a multiplication problem, it's a division problem. See, I call that algebra because what I see isn't what I get. You see, to be able to do this problem on the calculator, I am going to have to paraphrase it into a language that the calculator understands. See, the calculator also sees mathematics as a second language. It's programmed to receive information in a certain way. And if the information is packaged in a way that the calculator can't decipher it, we have the responsibility of paraphrasing it and translating it into the language the calculator can understand. You see, the point is, if we write the problem this way, then how do we handle this problem on the calculator? We enter 5.09861. Now, instead of pressing the times key, we press the division key. Then we enter the 3.14167. Then we press the equal sign, and we read the answer, 1.622898013. And that's really amazing. The place you really appreciate the calculator is in the division problems. Multiplication is bad enough, but can you visualize dividing place after place after place using a 6-digit divisor? Get on that calculator. In a second, so to speak, this all appears at once. But even with easy numbers, if you don't know what you're doing, the calculator won't help you. Let's come back to a problem that we've used before and we'll probably use again. It says fill in the blank, and I give you 3 parts. The first says 40 is blank percent of 80. The second says 40% of 80 is blank. And the third one says 40% of blank is 80. And if all you know is the calculator, you look blank. If you don't know the concept, you look blank the whole time we're talking about this. These 3 problems may look alike, but they are philosophically quite different. You see, the first says what? What part of 40 is 80? It's 40/80ths, which is 1/2, and as a percent, 1/2 is 50%. The second problem says take at a rate of 40 per 100, how many would you take out of 80? And that would be 32. See, because 40% is 2/5, 80 divided by 5 is 16, 16 times 2 is 32. The third part says 40% of what number is 80? Well, if 40% is 80, 1% must be 2, and if 1% is 2, 100% is 200. Look how different those 3 problems are, but if you don't understand that difference, how is the calculator going to help you? I've given quizzes like this, and students come up to me and say, I think you gave us the same problem 3 times. I say, tell your calculator. And if you're in doubt, sure, just pick whichever one is easier, write it down 3 times, and go for 1 out of 3. That usually wins a good contract in baseball. Well, at least for hitting, not for fielding. This is more like a fielding average. Learn to understand these things, because if you don't understand them, the calculator isn't going to help you. Let me show you another problem where if you know what you're doing, the calculator will help you. You see, in this course, you can buy any kind of a calculator you want. But if all you're going to do is use it for the arithmetic portion of the course, in other words, for these 12 modules, you don't need a very expensive calculator. All you need is a calculator that does the 4 basic operations: addition, subtraction, multiplication, and division, and something called taking the square root, which I'll explain to you in this problem over here. It says, to the nearest hundredth, find the number which, when multiplied by itself, equals 160. In other words, what number multiplied by itself equals 160? By the way, this is another thing that happens in mathematics. When we use a blank like this, we usually mean that the same number goes into both blanks. I'll explain that more when we get to algebra in Module 12. But basically what I'm saying is, what one number can I put into both blanks to make this a true statement? Well, let's take a wild guess. I'll try 12. 12 times 12 is 144. That was pretty close, but I'm too low on that, right? 12 is too small to be the right answer. I'll try 13. 13 times 13 is 169. That's too big to be the right answer. By the way, you don't even have to guess this closely the first few times. You could have said 10 times 10 is 100, which is too small, and 20 times 20 is 400, which is too big, and gradually refine. But do you see how messy this is going to be to try to find the correct answer to the nearest hundredth? You follow that? Well, the process, see, we've already mentioned that when you multiply a number by itself, that's called squaring the number. See, if I say to you square 9, that means 9 times 9, which is 81. If I say find the square root of 9, That means what number must you multiply by itself to get 9? So in this particular problem, I've asked you to find the square root of 160. That means the number which will multiplied by itself equals 160. And what I'd like you to do is to have a calculator which has a square root key on it. The square root key often appears as it looks like a division symbol with a hook on it. And sometimes the letter X appears inside, and sometimes it just appears like this. And on my calculator, when you want the square root of a number, you enter the number first, then you press this key. On some calculators, if you want the square root, first you press the square root key, then you press the number. But let's start with an easy problem. Suppose I want the square root of 25. Hopefully you all know what that number is. What number multiplied by itself is 25? It's 5, isn't it? Okay, so let's take a look here and see what happens. I enter the 5, I press the square root sign, and I read the calculator and 5 appears. And let's check it out. Is 5 times 5 equal to 25? Sure, but you didn't need the calculator for that. Let's try the calculator now on the problem we just talked about. What number multiplied by itself gives you 160? Well, we enter the 160, we press the square root sign, and what do? We read 12.649110064. In a second, this whole thing lights up, and there is the square root to all these decimal places. I said find the answer to the nearest hundredth, so we go to the hundredths place, look at the digit immediately to the right. That's more than 5, so we round this up to a 5, and so the answer is 12.65. And just as a rough check, if you take 12.65 and multiply it by itself, you get 160.0225, a pretty good approximation. The real big difficulty, as we'll see starting in Chapter 11 especially, and also in Module 12, the difficulty will not be taking square roots, it will be knowing when to take the square root. But we'll talk about that more later. Now, the other thing a calculator doesn't do for you is help you find remainders. See, sometimes you have to learn to understand that every answer on the calculator is given in decimal form. Let's take an easy problem just so I can explain the concept, one that you don't need the calculator for. It says use the calculator to find the remainder when 26 is divided by 4. Well, that's a pretty simple problem. 4 goes into 26 6 times with a remainder of 2. The remainder is 2, isn't it? Do the same problem on the calculator. If you do this problem on the calculator, enter the 26, press the division symbol, hit the 4, hit the equal sign, you get 6.5. The remainder can't be 5. When you're dividing by 4, the remainder can't be more than 3. The way you read this is that it's 6 and a fraction, in fact 6.5. 6 times 4 would be 24. Then you could subtract the 24 from the 26 to get that the remainder is 2. See, that 0.5 is not the remainder. It's the fractional part of 4 that's left over. In other words, 6.5 means 6 plus 0.5. By a distributive property, the 4 has to multiply the 6. That's where you get the 24 from. Then the 4 has to multiply the 0.5. 5 times 4 is 20. Move the decimal point one place. There's your 2. And that gives you 24 plus 2. And that's your remainder. Okay? And I wanted to emphasize that because let's do this in the form of a word problem. Maybe it'll be easier for you to see. So you have $26 to spend on ties that cost $4 each. How many can you buy? Well, the calculator says 6.5 ties. But that means what? 6 ties plus half of a tie. But when we change the label to money, a tie is the same as $4, so half of a tie is $2. It's sort of like people say you can't divide 3 by 2 and still get a whole number. But suppose a father left 3 racing horses to be divided equally between 2 children, and they couldn't kill any of the horses. How could they share them equally? Well, what they could do is keep one each and sell the third one, so that converts the horse into money, then split the money. You see, there are different ways of counting. But I just want you to see that even with the calculator, you still have to do a lot of thinking. But the most important point is that the thinking part isn't always easy. And I thought that this far into the course, I would like to do something that was meaningful, but also fun. I thought I would like to show you some of these mathematical devices that you can have a lot of fun with your friends with, because the answers are things that most people just don't think about. There are many other examples I could give. I've just picked a few to fill in the time for this particular lecture. There are books, in fact, called Mathematical Recreation, Famous Brain Teasers. There's all kinds of books in which the answer that seems right is completely wrong. Here's one. You have some stock, and the stock increases, rises 50% one week. But the next week, it falls 50%. What's the net result? If you weren't expecting a trick here, you would blurt out, we broke even. And you wouldn't even bother using your calculator, because what's the sense of using a calculator on a problem this simple? The trick is percents. Remember, numbers in this course are adjectives modifying nouns. The 50% the first week is modifying a different amount than the 50% the second week. And rather than argue philosophically about this, let's just pick a number and see what happens. Suppose you start with $100. If the stock increases by 50%, that means it goes up by half its value. Half of 100 is 50, so at the end of 1 week, it's now $150. Now it decreases by 50%. But what's the part that's decreasing? It's the 150. See, 50% is half. You're losing not half of 100, but half of the 150. That leaves you with what? $75. So you started with $100. After the 50% increase, you had 150. Then when that decreased by 50%, you had 75 left. So the net result was that you lost $25 out of your 100. It may have sounded like you were breaking even, but you just lost 25%. You know, that's how gambling houses make a living. They don't have to be dishonest. They got too good a thing going for them. They have games where the odds are in their favor, but as you listen to them, you think they're in your favor, so you keep playing, and you're losing because the odds are against you, but you keep playing because you say, hey, the odds are in my favor, and they're going to change. Learn how to count properly with or without the calculator. We're going to do a lot more problems like this as today's lecture goes on. I just hope you enjoy these. I just think they're fun. Here's one where the average answer that people give is so ridiculous, but they still blurt it out anyway. John can paint a fence in 8 hours. Bill can paint the same fence in 4 hours. How long will it take if they work together? Do you know what people tend to blurt out on this? They look at the 8, they look at the 4, they say, we'll split the difference. 6. Takes 6 hours. How can it be 6 hours? The faster guy does it in 4 hours by himself. I remember when I first told my father that story, he says, well, that's what happens when you have somebody working with you. You talk, you have coffee breaks. He didn't see anything funny about this at all. And by the way, he was quite right. You know, I want to show you how you do this problem the correct way. But as I do it, I also want you to see what kind of assumptions are being made here. I mean, can you see what I'm saying, though, that the answer can't be 6 hours? Because if Bill was working by himself, it would only take him 4 hours. Obviously, John should be helping him. See, the way the thing works is, if you do the job in 8 hours, in 1 hour you do 1/8 of the job. If you do the job in 4 hours, in 1 hour you do 1/4 of the job. So in 1 hour working together, you get 1/8 plus 1/4 done. That's 3/8 of the job each hour. So in 2 hours you do 3/8 twice, which would be 6/8. So in 2 hours you get 3/4 of the job done. In 3 hours you would do 9/8, which is more than the whole job. So the whole job would take what? Between 2 and 3 hours. The reason that my father's way of doing this problem wasn't so far off is, what's the likelihood that if you paint a fence in 8 hours, that you're going to do in 1 hour 1/8 of the job? See, it's an average thing again. Do you work at the same rate? Is it possible that you painted half the fence in the first 2 hours, then get tired and took the remaining 6 hours to finish? Is it possible that John and Bill only have one paintbrush between them? In which case, the best strategy is what? Give it to the faster guy and let him go. See, think of all the assumptions that are made in the math problem. That's something I thought you'd like to hear about. Because people say the nice thing about a math problem is there's only one answer, it's cut and dried. And the answer to that is, yes, thank God, there is only one answer, but only after you've analyzed the problem correctly. You have to understand what we call a mathematical model, and I'm trying to teach you all of these things gradually so that if you stay with me through our sequence, and we go from arithmetic to algebra to advanced algebra to trigonometry to calculus, it will all seem like a continuation of the same subject. And that's the way learning should be. It should be like life. You look back over a 10-year period and things have changed a lot. But yet on a day-to-day basis, you hardly notice any change. That's what learning should be like. It should be a very pleasant thing where day by day you seem to be making no progress, but then you look back and say, wow, how did we get to Module 9 already? That's the way it should be. But enough about that for the time being. Oh, let me show you another way of doing this problem using the dimensional analysis that we talked about. See, if you can do 3/8 of the job, see, the 3 is modifying the job here. See, 3 times the job divided by 8. If you can do 3/8 of the job in 1 hour, how long will it take to do the whole job? So you have one job equals blank hours. So to get rid of jobs over here, you put it in the denominator, put hours in the numerator. You see, the jobs will cancel. So it's going to take you what? 8 over 3, which is 2 2/3 hours. A third of an hour is 20 minutes. So the job, if things work utopianly, in other words, if they all work at the same rate, and they don't bother each other, and they both have their own paintbrush, in 2 hours and 40 minutes, they'll finish the job. Now, why did I put this problem in here? To show you that if you have a calculator, but don't understand what you're doing, you can't do this problem. If you don't have a calculator, but you do understand what you're doing, it's a 2-step problem. Here's another great one that people always get wrong until you tell them it's a riddle. That's the amazing thing. If a person is going up for a doctoral examination in math, and you're the person who's questioning them, if you say to that person, how much is 2 and 2, they are going to say anything except 4, because they say, this is a doctoral exam, he wouldn't ask me something that easy. So once you tell somebody that something is a joke or a riddle, they shy away from the obvious answer. But pretend I didn't tell you this was a riddle. See what answer you would tend to blurt out here. You travel for 60 miles at 30 miles an hour. Then you go 60 more miles at 20 miles an hour. Okay? You went half the distance at 30, half the distance at 20. The question is, what's your average speed for the 120 miles? So you say, well, that's easy. I'll just average the 20 and the 30. That will give me 25 miles per hour. You can do that either with a calculator or without. But whichever way you do it, that's the wrong answer. Believe it or not, the average speed here is not 25 miles per hour. And what's nice about this is that we can check it out. Look, 60 miles at 30 miles an hour is going to take 2 hours, isn't it? 60 miles at 20 miles an hour is going to take 3 hours. So going the first 60 miles takes 2 hours. Going the second 60 miles takes 3 hours. So altogether for the round trip, not the round trip, for the 120 miles, you spent what? 5 hours. You went what? So let's just add this up. You went 60 and 60 is 120. 2 hours and 3 hours are 5 hours. So you went 120 miles in 5 hours. And 120 miles divided by 5 hours is not 25 miles per hour, it's 24 miles per hour. And don't go looking in the street now to find where that extra mile per hour went. It didn't go anyplace. The thing that people overlook in this problem is that since you traveled the same distance at both speeds, it's going to take you a longer time at the slower speed. In other words, you're traveling for 20 miles an hour for 3 hours, and for 30 miles an hour just for 2 hours. See, the time the answer would have been 25 miles per hour would have been if you traveled the same time at both speeds. Let me give you an example in your own life. Let's suppose you get 100% on one test and a 0 on another test. What do you expect your average to be? No tricks involved. 50%, right? 100 and a 0 average out to a 50. But what were you assuming there? You were assuming that the 100 and the 0 were equally weighted. What if the 100 was on the final exam and the 0 was on a 1-minute homework quiz and your teacher is a decent, sane human being? Do you really expect the average to be 50, or do you expect the 100 in the final exam to count considerably heavier than the 0 on the 1-minute homework quiz? You see the idea? To take the traditional average, things have to be equal. And you didn't drive the same amount of time at 20 miles an hour as you did at 30 miles an hour. See, for example, you went what? For 2 hours at 30 miles an hour? That was 60 miles. If you had gone for 3 hours at 20 miles an hour, that would have been 60 miles also. Now you would have traveled 120 miles in what? You would have traveled 150 miles in 6 hours. I mixed that up a little bit. Let me just go over it so nobody's confused by that. Suppose you traveled for 2 hours at 30 miles an hour. See, that's 60 miles. Now you travel for 2 hours at 20 miles an hour. I mixed up two things here. That's 40 miles. So altogether you've gone 100 miles and it took you 4 hours. That's 25 miles per hour. See, the reason it averaged out there was you traveled the same amount of time at both speeds. Hope I didn't confuse you too much with that. But that's okay. The important thing I wanted you to see is that you won't get the right answer using the calculator if you don't understand the concept. Here's one that's even more mystifying. You're going to travel 2 miles. It's like a racetrack qualification thing. You have to do 2 one-mile laps. And to qualify for the race, you have to average 60 miles an hour for the 2 laps. So here's what happens. You travel the first mile at 20 miles an hour. You're not sure of the track. You want to be careful. You know you can go as fast as you want, so you don't mind squandering the first mile. So you go the first mile at 20 miles per hour. You have to average 60 miles an hour to qualify for the race. So how fast do you have to travel the second mile in order to average 60 miles per hour for the 2? Excuse me about that. This is just not one of those days. I hope my wife is watching this program and has some strong coffee for me when I come home. Okay? 2 miles. See, you go 1 mile. The first mile you went at 20 miles per hour. How fast do you have to go the second mile in order to qualify for the race at 60 miles per hour? Would you believe it's impossible? The most common wrong answer I get is 100 miles an hour. They say, look, you want to average 60. You did the first one at 20. That was 40 miles too little, so now we'll add 40 on to make up for it. Let me show you a little trick over here. 60 miles per hour means 60 miles per 60 minutes, doesn't it? Per means divided by. 60 divided by 60 is 1, and the label is miles per minute. You're going 1 mile per 1 minute. So in 2 minutes, you go 2 miles, don't you? See, multiply both sides of the ratio by 2, so you're going what? 2 miles per 2 minutes. That means that to qualify for this race, you have to do both miles in a total of 2 minutes. Now, how fast did you do the first mile? The first mile you did at 20 miles per hour. That's 20 miles per 60 minutes. Divide both sides of this ratio by 20. Remember, we can multiply or divide both sides of a ratio by the same number. What does that tell you? You went 1 mile per 3 minutes. You're only allowed 2 minutes altogether. You've already used up 3 minutes on the first mile. Is that amazing? In fact, if you were Superman or better, and they allowed you to travel the second mile with no time elapsing, since you've already used up 3 minutes for the first mile, unless you invent negative time, which we don't talk about until next semester, the best you can do is 2 miles in 3 minutes. But at the rate of 2 miles per 3 minutes, that's 40 miles per 60 minutes, which is 40 miles an hour. Would you believe that? If you spend the first mile going 20 miles per hour, no matter how fast you go, you will never even average 40 miles per hour for the 2 miles. Don't get me wrong. If you did enough laps fast enough, eventually you could bring your average up to 60 miles an hour. But you can't do it with just 1 lap left. There comes a time in life, and we're talking about this before the program with some of the crew, that you can say things like, I'll make this up tomorrow, or in a baseball game you say, we still got 4 innings to catch them. There comes a time when you've lost your last chance to catch them. And you've got to be very, very careful in timing things to make sure that you don't let time run out. And this is a classic example based on that. And the exciting part is what? It's a fun problem, and the calculator wouldn't even warn you that you were making a mistake because you would have been using the wrong reasoning. Here's the all-time classic. You can tell it's an old problem by what the 3 men are paying for the hotel room. I mean, to get 3 men into a hotel room for $30 today, I mean, you just can't do that anymore. I just went to a restaurant in one of the local hotels, all you could eat for $700. It was terrible, but let's not worry about that. When this riddle came out, this was a high-class hotel. It says 3 men pay $30 for a hotel room. Okay? So they each paid $10. When they got to the room clerk checked and found out that the room was only supposed to be $25. So he gave the bellhop $5 and he says, look, these 3 gentlemen who just checked in overpaid by $5. Would you please give them back the $5? Now the bellhop never took this course. So he didn't know how to divide 5 by 3 equally. So he did it pragmatically. He said, look, these guys aren't expecting anything back. So I will keep $2 for myself, and now the remaining 3, I'll give them back 1 each. He says, I'm happy because I got the $2. They'll be happy because they get $1 back, and everything will be fine. So now, let's see how this problem goes. They paid $30 for the room. The bellhop was told to return $5 to them, but the bellhop keeps $2 and gives each man back $1. Now the reasoning goes like this. Originally, each man spent $10. He got $1 back. That means he paid $9, right? But there were 3 of them. So $9 each. 9 times 3 is $27. But there's also the $2 the bellhop kept. $27 and $2 is $29. And the question is, what happened to the other dollar? I have kids out all over the street now looking for it. They're not going to find it. And you know why they're not going to find it? No, not because they're not looking. Because there is no extra dollar. Here's a perfect example of doing the arithmetic correctly, but you're doing the wrong arithmetic. Let's just check this thing through to make sure we're doing it right. The 3 guys paid $30 between them equally. Is 30 divided by 3 10? Yes. They each got $1 back. Is $10 minus $1 $9? Yes. Is 9 times 3 27? Yes. Is 27 plus 2 29? Yes. Therefore, since all the arithmetic is correct, the calculator isn't going to help us solve that problem. What did we do wrong with this problem? You know what we did wrong with this problem? We got psyched out of our skulls. We really believed that there was $30 to account for. Let me tell you something. Did these guys pay $30? No. When you pay something and you get change back, isn't what you spent the difference between what you paid and what you got back? If I go into a store and buy a package of gum and I give the clerk a $5 bill, can I say I spent $5 for the gum? Only if he doesn't give me change. If he gives me change, I subtract the change from the $5, and that's how much I paid, isn't it? See, when these guys paid the $30, didn't they each get back $1? Once they each got back $1, they only spent $27, didn't they? 9 times 3 is 27, isn't it? That's what they spent. The $30 is gone as soon as they got their change. You see, what the problem should have said was, they paid $30. The bellhop gave them back 3, which means that they still spent what? $27, of which the bellhop kept 2, and the 25 went for the room. You see, if the bellhop hadn't taken a self-inflicted tip, the guys wouldn't have spent $9 each. The $9 each already included the 2 the bellhop kept. Now, this is an exciting brain teaser. On radio talk shows, at least once every 3 or 4 years in the Boston area, somebody calls in and asks the talk master this question and how to solve it. And I never call up to give them the answer because I love to hear people trying to find the dollar. But what's wrong here? It's something that the calculator can't help you with. It's called a number sense and awareness. Okay? And there are other problems that are just as serious. Here's one that happened to me when I was teaching at a community college in upstate New York. I said, an outfit, this is a story right from there. An outfit consists of a pair of slacks and a jacket. How many different outfits can be formed from 2 jackets and 4 pairs of slacks? Well, you see, basically the way the problem goes is, let's call the jackets A and B. And by the way, these are used in statistics, these kind of diagrams, and in probability. You count the outcomes. Let's call the jackets A and B, and let's call the slacks 1, 2, 3, and 4, for purposes of identification. See, the letters will refer to the 2 jackets. The numbers will refer to the slacks. The person can pick either jacket, can't he? He can pick either jacket A or jacket B. Once he picks the jacket, can't he still pick any one of the 4 pairs of slacks? You see, he can pick jacket A and match it with slacks what? 1, 2, 3, or 4. Or he could have picked slacks B and matched it with jackets 1, 2, 3, or 4. In other words, there are 8 combinations. Do you see how to read these? A1, A2, A3, A4, right? See, the first jacket with the first pair of pants, first jacket with the second pair of pants, first jacket with the third pair of pants, first jacket with the fourth pair of pants. He could have also picked what? The second jacket and paired that with the first pair of pants, second pair of pants, third, and fourth. You see the 8 combinations here? Now, is 4 plus 2 6? Here's what happened. The right answer to this problem is 8. You multiply the 4 by the 2. I had a student come up to me and say, are you sure you went to MIT? I said, that's right. He said, well, how come you don't know how much 4 and 2 is? I said, 4 and 2 is 6. He says, well, I wrote that on my paper, and you marked it wrong. Well, you see, the question wasn't how much is 4 plus 2. You see, and even if he had a calculator, if he entered 4 plus 2 in the calculator, would he have got 6 for the answer or 8 for the answer? He would have got 6. You see, in this particular problem, even though 4 plus 2 is 6, the correct answer is what? 4 times 2. Why? Because that's the way it comes out. See, any one of the 4 pairs of slacks can be matched with any one of the 2 jackets. That's like the distributive property. See, each of the 4 pairs of pants distributes with each of the jackets to give you a total of 8 combinations. And what's nice here is that you can count them. See, so the answer is 4 times 2, not 4 plus 2. The calculator, if you put in 4 plus 2, wouldn't say to you, hey, that's dumb, man, you want to multiply. Calculator just does what it's told. And in fact, this whole idea leads to something called permutations and combinations, which is a very heavy topic in finite math, in discrete mathematics, in college algebra, and surprisingly enough, in calculus in certain areas, but really in probability and statistics. And let me give you just a minor problem that way. It says how many 4-digit numbers can be made up by using each of the digits 1, 2, 3, and 4 once each. In other words, I have these 4 digits, 1, 2, 3, and 4, and I'm going to rearrange them. I've got to use each of those 4 digits once. See, I can't write down 1,111 because I'm using the 1 4 times, and I'm not using the 2, 3, or 4. I have to use the 1, the 2, the 3, and the 4, okay? And the question that comes up is, how many different 4-digit numbers can I form that way? Now, obviously, people can say, well, let's see, there's 1, 2, 3, 4. I'll add them up. That gives me 10. Well, 1 plus 2 plus 3 plus 4 is 10, but it's not the right answer to this problem. The question didn't say how much is 1 plus 2 plus 3 plus 4. It said how many 4-digit numbers can be formed. And let me show you how that problem works. See, let's call this the first digit. I'll put in 4 blanks here. The first digit, the second digit, the third digit, and the fourth digit. Can't any one of my 4 digits be chosen first? And once that first digit is chosen, can't any one of the remaining 3 be chosen next? See what I'm saying here? I can choose the first digit in 4 ways and the second digit in 3 ways. Now, why do I multiply over here? Let me just go on to the next line here so that you can see how this looks in terms of a picture. You see, I'm saying what? The first number I pick can be either 1, 2, 3, or 4. If I pick 1, what choices do I have for the second number? Remember, none of the digits can be repeated. So once 1 is chosen, I have 3 choices, namely what? 2, 3, and 4. Once 2 is chosen, I can only have what? 1, 3, and 4. Once 3 is chosen, I can only have what? 1, 2, or 4. I can't use 3 again. Do you see how to read this okay? See, if I pick 4, what 3 numbers are left? 1, 2, and 3. So which one could be second? Either 1 or 2 or 3. And if I stop over here, what this says is, just using the first 2 digits, I can have something that begins with 1, 2, 1, 3, 1, 4, 2, 1, 2, 3, 2, 4, 3, 1, 3, 2, 3, 4, 4, 1, 4, 2, 4, 3. And what I'm saying is, after you've done that, can't the third digit now be picked in 2 different ways? For example, if you're following this chain over here, what have you used up so far? A 1 and a 2. So what possibilities do you have for the next one? It has to be either a 3 or a 4. You see what's happening? There are what? 3, 6, 9, 12. There are 12 little roots here. And now from each of these roots comes 2 more. There's going to be 24 altogether, which is exactly what you would get if you said what? 4 times 3 is 12, times 2 is 24. And by the way, once you've chosen the first 3 numbers, there's only one way to choose the 4th number because everything else has been used up. And by the way, if you don't believe me over here, you can actually list what the 24 are. I've done it for you simply to show you that it's tedious, but it can be done. See, for the person who says you can only make up 10 of these things, I've already proven that he's wrong. Because just look at the first, I've written them in rows of 6 here. See, there's 6 here and 6 here. There's 12 different ones right there, so how could 10 be the right answer? But here's 6 more, and here's 6 more. But the exciting thing about math is you don't have to list them. I mean, what if I had 50 digits and wanted to arrange them? I mean, do you realize how long this list would be? Or even in this problem, suppose I said I could use any one of the 4 digits as often as I wanted. In other words, I could write 1,111. I could write 2,122. See, I could use any digit as often as I wanted. Watch how cumbersome the problem becomes now. You see, now, after I pick the first number, which can be done in 4 different ways, I can still pick any one of the 4 for the second number, any one of the 4 for the third number, any one of the 4 for the fourth number. So altogether, how many choices do I have? 4 times 4 times 4 times 4, which we write as 4 to the fourth power. See, don't confuse that with 4 plus 4 plus 4 plus 4. That's only 4 times. See, when you add 4 4s, you get 4 times 4. When you multiply 4 4s, that's that exponent thing. You get 4 to the fourth power. And how do you read this? 4 times 4 is 16, times 4 again is 64, times 4 again is 256. It would take you 200, you would have to find what? Actually, to list the possibilities, there are 256 such numbers, just from what? The digits 1, 2, 3, and 4, making 4-digit numbers. Now, that basically brings us to the end of what I wanted to show you today. I want you to take the textbook, the study guide, and familiarize yourself with how to use the calculator. I really want you to go out there and get a calculator. You can buy one for as little as $7 or $8 that will do what I want you to do with it. You can buy one that will do almost everything you want for well under $50 today. And the more you go on in math, the more the calculator will return to you. In fact, a lot of people are buying personal computers now. I'm just at the stage now where I prefer to have students have a calculator just to free them from the process of doing long, laborious work and freeing their minds to do the exciting stuff. In other words, we'll look at the calculator as the slave that does all the dirty stuff, and we'll do all the exciting stuff. But the price that you have to pay to do that exciting stuff is you have to understand the concepts. You see what I'm saying? I've used this example before. If you know that 9 times 3 is 27, but if I say to you, at $9 each, how much will 3 handkerchiefs cost? And you say, I can't do word problems, then you really don't know how to multiply 9 by 3. And in terms of that example, which I've used before, what I'm saying is with the calculator, if you forgot what 9 times 3 was, you could punch in the 9, the times sign, the 3, and the equal sign, and get 27 for the answer. But if you've forgotten that you're supposed to multiply 9 by 3, then you're in trouble. The calculator won't help you. And again, there will be times when I repeat things that I've said. One of the most common remarks I hear from students who survive math courses is they heave a big sigh of relief and they say, wow, I could do everything except the word problems. And the irony is that in real life, most people are taking math to be able to do the word problems. If you have a calculator and you use it incorrectly and you find the right answer but to the wrong problem, as I've said before, that's the same thing as finding the wrong answer to the right problem. So before you start turning yourself loose on the calculator, first of all, make sure that you understand what the operations of arithmetic mean, learn how to estimate, learn how to get a feeling for what a reasonable answer is. And I think that's enough of a harangue for one session, so we'll call it a day for now. I'll catch you all again next time. Until then, have fun, keep studying, and stay young.